So as you know, now we are moving on the new topic starting from today. So we are going to learn how to integrate into dimensions. So in the book, if you look at the book now, so you're gonna see chapter 15. This is called multiple integrals. So multiple integral means, like integral in more than 2 dimensions. Uh, Here, what we going to learn? We're gonna learn double integral over rectangles, which is the easiest one. And then after Songkran, we're gonna come back and learn iterated integrals and then double integrals over several regions. The last one that we're gonna learn, we're gonna trying to move to double integral in polar coordinates. That is all the topic that we're gonna cover for this class, which gonna take today and 2 more weeks, and then that's gonna be all for the final exam. So we're gonna just test you how to do the basic differential equation, basic differentiation, and also basic double integration. Okay, so that is all the content that we're gonna learn for this class, which it gives you a strong background, for sure enough background to study more science and technology topics later. Okay, so first of all, let me review you a basics from calculus 1. So, well, let's take a step back and recall what you learned in Cal 1. So I assume that everyone now already forgot about this thing. So let's brush up this thing and, look at it again. So suppose that you have fx. So the one that I highlight in green now, this is my function fx. Well, let's suppose that you have a function y equal to fx. And you know that your function fx is greater than 0. So let's make it easy first. So look at the case that fx is positive. So the graph of fx now is above the x-axis. So in calculus 1, you learn this notation. Integrate, which is look similar to brain spout. Integrate from a to b fx dx. And when you learn Cal 1, Ajahn Ratinan told you that, hey, the meaning of this thing, this is the area under the curve fx from a to b. That's right. Is that right? So which means the one that I highlight in blue here, this is called integral from a to b, right? The meaning of this thing is area under the curve f from a to b, from x equal to a to x equal to b. Well, basically, this is the one that we are talking about, the one that I highlight in light blue here. This is the meaning of integration in 1 dimension. So first of all, we're gonna look at the meaning of integration in 2 dimensions first, and then we're gonna go to the examples. Okay, so we're gonna shift the idea from area to volume, because here you have area, because this is you have x and y. So it's gonna be, if you have x and y, it's gonna be just a plane, like xy plane, xy axis here. But now if you move to double integral, which we're gonna talk in few minutes, so you're gonna need the x-axis, you're gonna need the y-axis, and you're gonna need the z-axis. So basically you are looking for the volume, because once you have the function of 2 variables, the thing that is under here gonna be a volume, not just an area. So you're gonna see in few minutes. But here, this is the idea that in 1 dimension we have an area. So 2 dimension, we're gonna cross this thing out. We're gonna call it volume because it's gonna be in 2 dimensions. Okay, and some of you are gonna be curious about the formal definition. This is the formal definition that you learn in Cal 1, right? But no one uses the formal definition, because when you integrate, you always use the formula. Because the formal definition is, well, if you remember, well, we're gonna look at the area under the curve here from A to B. And then you're trying to chop up A and A to B here. This is the x-axis from A to B. You're trying to chop up A to be into, let's say, n pieces. So you chop up into n pieces. Well, with this picture, they chop up like S1, S2, S3, and so on up to Sn. And then for each stack, what are you trying to do is you're trying to compute the volume, or not the volume, for one dimension, it's going to be the area. So you're trying to compute the area for each stack, and then you sum it all. So you're going to get the area. This is what they're trying to do here with this formula. So they're trying to, well, compute the area for each stack, which means they're going to use the delta x, which is going to be the width for each stack. And then they're going to multiply the height of that stack, which is going to be fx star. Well, they just define x star and doing that thing. Well, you get this. So when you do fx star and delta x multiply together, you get the area for one stack here. And then you do it for every single stack here. So that means you sum it all. And then you take limit when n go to infinity. That means you're trying to chop it up infinitely many times, like make it more and more and more, like frequent. At the end, you're gonna get infinity, and the separation from A to B gonna be infinite. And then that means you're gonna get the area under the curve. This is the idea from Cal 1. And we call this thing Riemann sum. If you remember, when Ajahn Ratinan taught you in Cal 1, we talked a bit about Riemann sum. But you know, in real life, this is not what we use, because Riemann sum is hard to use, because you can see that you have to compute summation, which you know you are not good at series. And then you have to take limit. This is not good. It's gonna take too long to do that thing. So we have a fundamental theorem of calculus. So the fundamental theorem of calculus say that, well, if you want to integrate from A to B fx dx, we could find the antiderivative, capital F, and then we're gonna do fb minus fa. So let's find the antiderivative, and then plug in at b, plug in at a, and this is what you do in Cal 1. This is what we usually do in real life, okay? Which means you're gonna need to learn how to get the formula, the antiderivative formula of f, well, which is this one. This is the formula that you learn in Cal 1. We're gonna need to keep it because we're gonna use it again in Cal 2. Because we're trying to avoid Riemann sum. We are not going to use the Riemann sum approach. We're gonna use the formula approach, which means you need to memorize this thing. So the thing that you need to memorize is 1, 2, 3, 4. Well, this is the one that you use again and again. So you have to. Something like integrate 1, you get x, integrate x to the r, you get x to the r plus 1 over r plus 1, integrate cosine, you get sine, integrate sine, you get negative cosine. This is the thing that you can you use again and again and again. Well, number 5 to number 11, this is this show up not frequent as 1 to 4, but sometimes you need to use it. So integrate secant square, you get tan, integrate secant, you get sec. This one, like very rare that you're gonna see. Integrate cosec, you get negative cot. Integrate cosec cot, you get negative cosec. This is not often, you know. And number 9, 10, 11, this is the formula that related to inverse trigonometry. So which, you know, hard to see, you know, you don't see it a lot. Well, the one that you probably see it a lot is 1 plus x squared. 1 over 1 plus x squared, this is going to be R10. Okay, there are also another 2 formula that you use a lot, which is integrate e to the x, get e to the x dx, you get e to the x plus c, and also another one is integrate 1 over x dx, you get log absolute x plus c. This is the one that you use a lot. Well, keep in mind that when we talk about the formula number 2 here, we mean x to the r, where r is not equal to -1. Okay, this is r not equal to -1, because if r equal to -1, the denominator is gonna be 0, and that is uncomputable. So not clear, right? So when I equal to -1, go for logarithm formula. So this is all the thing that you need to know about the basic in Cal 1. Okay, so we're gonna keep this formula because you're gonna need it to integrate into dimension as well. Okay, so that's all the basics. So now let's talk about double integral over rectangles here. So this is what you have. Well, into dimensions, as I told you that before, that when you have c equal to fxy, this is no longer a line, everyone. No longer a line. This is called a surface. So when you draw a picture of fxy, it's gonna be a surface. And when it is a surface, so you cannot say the area under the surface. It does not make sense. So the thing that is under the surface, it must be a volume. Well, let's look at that. So we're gonna start from, well, let's say that, well, we're gonna project the surface here to R, which is going to be the base at the XY plane here. You project the surface into the area called R. So you're gonna define R to be interval AB cross CD. So again, AB here, this is going to be the one side of the rectangle here. CD here gonna be another side of the rectangle here. Basically, your AB cross CD here gonna be your base. Okay, and when you do the integration over rectangle, it means when you do the integration fxy into dimension dx dy, this is the notation. So you're gonna integrate 2 times. So x first and then y. You're gonna say x from A to B and then y from C to D. So first of all, you need to look at the notation here. So x is inside, so we're gonna integrate x first. So x from what to what? So x from A to B. Okay, this is the x-axis. So you're gonna integrate x from A to B, which is the one that I highlight in light blue. And then next, we're gonna integrate, well, let's take another color. Well, let's say yellow. So y here, you're gonna integrate y from C to D. And then here gonna be another side of this rectangle R. You know, so this is actually the meaning of double integral over rectangle. If you find this thing, so it's gonna give you the volume under the surface C equal to fxy. Why? Let's take a look. So first of all, you can, from R here, okay? You can draw R here in a nice plane. So this is your R. So you're gonna do the same thing as you did in calculus 1. So you're gonna chop up the x-axis from A to B into small, let's say, how many pieces? So they say M pieces. So let's chop this thing up to M pieces. And let's chop this thing up to N pieces. And you're gonna get the table like that, like the cross table here. And for each time, for each small rectangle here, you can compute the volume by, looking at the small pieces here. And then this is going to be one stack as well. One stack here. And then you're gonna compute the volume for one stack first. And then once you compute it all, every cell here, you sum it up. So you're gonna get a picture like this. Does it make sense? So basically you are looking at delta A. Delta A gonna be just, the area under the curve here. The area for one grid here, just one grid. And then you multiply fx star y star. This is the height that you pick. And then once you multiply this and delta A, well, you're gonna get the volume for just one stack. And then you sum it all because you want all stacked together. Let's sum it all. And then you're gonna get this thing. Okay, this is not smooth, right? You can see that it's still like have a discrete thing on the top because you can see that Yeah, I mean, the top is not smooth. It is not a surface yet. Well, how do we make it smooth? Well, you have to chop x and y axis continuously. So if here's 1, 2, 3, 4, 5, 6, 7, 8, you only chop y axis to 8 pieces and you only chop x axis to 5 pieces. So if you increase the number of separation, like I have 800 times here, 500 times here, so the stack gonna be more continuously. And at the end, well, once you sum it all and then you take limit, which means you're gonna make it smooth. So at the end, you can see here, this is the surface here. If you do only a 2 by 2 stack here, it's gonna be just, well, the area of the volume that you get, sorry, the value of the volume that you get, this is not correct to be the under, to be the, you know, the volume under the curve, because it's just, it missed a lot, because you miss a lot of, there are a lot of space here, so that you cannot fill in. But if you increase your m and n, your approximation is getting better. Well, if you do more, so it's better. You do more 16 times on each side, you get more. So that means if you take limit when m and n go to infinity, the curve gonna be smooth, and at the end you're gonna get the volume under the curve here. That is the meaning of integration into dimensions. Why does it import? You know, how do I say? Well, I taught you this thing because this is going to be a good example to relate with your life. You know, because when you work as a biotech student, maybe you're gonna face a volume of the shape or something that you don't know about, or you don't know exactly what equation is or something. Well, if you can get just a surface of this thing, just only one part, just a surface, only one part of your solid or something like that, well, you can just take a guess or an approximation of the equation of the surface, and then now you can apply the integration so you can get the volume. You know, this is one application. And for sure, if some of you have to work with some three-dimensional shape or some kind of geometric shape, you know, in 3 dimension or something, well, you have to work with double integral for sure. This is why they force you to learn this thing to be a basic when you see it, so you don't be scared about it, and you can read, and then you can trying to understand it from the basics. Okay, for this class we are not going to focus on the interpretation, so we're gonna teach you how to calculate the integral here, which means you're gonna learn how to obtain this thing by using the formula, not the Riemann sum. But keep in mind that the basic start from Riemann sum. So because of the Riemann sum here, it tells you that the meaning of the double integral, this is the volume under the surface C equal to fxy. Okay, let's go. Well, this is, I already explained this thing. So when you integrate into dimensions, well, the thing that you write inside here, you have to integrate first, and then you can integrate outside after. So you can put dy inside as well, it's okay. And then when you put y inside, you have to integrate y first from C to D. If you put x outside, you have to integrate x the second time, and then x from A to B. You know, the location is important because the location of C, D, and A, B gonna tell us what value that we need to integrate with respect to. Well, the idea of integration is the same as as you learned last week for differentiation. If you see the y, integrate with respect to y, keep x constant. If you integrate the x, it means you integrate with respect to x, keep y constant. Okay, let's go. Okay, example 41. So I want you to evaluate double integrals 16 minus x squared minus 2y squared dA, where r equal to 0 to times 0 to. What does it mean? It means that you're going to integrate x from 0 to 2 and y from 0 to 2. Okay, which means the integral sign here can be evaluated as double integral 16 minus x squared minus 2y squared. Well, you can pick the order of integration as you want. Let's say I'm gonna pick the x dy. If I pick the x dy here, so I say x start from 0 to 2, y start from 0 to 2. Well, that's the first step. So you know this makes no difference because x and y, they are on the same interval. But let's suppose that if I change the equation to 0, 1 here, so you're gonna need to indicate 0, 1 here. You know, but well, this is the very first example, so I'm gonna just keep it simple like that. You know, if you feel like, Ajahn, I don't know what it is in real life, well, it's actually mean in 3 dimensions, c, y, x. Well, you are focusing on x from 0 to 2, y from 0 to 2, and let's suppose that you have a surface C. Well, the surface called 16 minus x squared minus 2y squared here. Well, this is not a good picture because the surface is not like this picture. If you draw a good picture, well, let's say I don't care about the shape of the surface here. So it's 16 minus x squared minus 2y squared. And then, you know, the volume under the surface, that thing, the volume under the surface, this is what we call integration 16 minus x squared minus 2y squared dA over r. Okay, sounds good. Well, but you know, this is the geometric interpretation which you can relate to your real life. But here, let's start looking at the calculation. So first of all, I do not need to touch the outside part. You can see that I keep 0 to 2 dy. The thing that I highlight in light blue here, do not touch it. It's like outside one. Keep it there. Work with the thing inside first. That is your technique. Please. And then, well, let's start by looking at this thing. So 16, you integrate with respect to x, you're gonna get 16x. X squared, well, 16, integrate with respect to x, you get 16x. X squared, integrate with respect to x, you get x cubed over 3. 2y squared, integrate with respect to x, you get 2y squared x. And then evaluate x equal to 0 to 2. Does it make sense? Well, I look at y here as a constant, so that is why I integrate this thing, so I get 2y squared x. Well, if you understand differentiation, this is nothing new. So you use this technique already in differentiation. Okay, and then, well, again, you evaluate the inside thing first, so the term don't look so messy. So you're gonna have 32 minus 8 over 3 minus, so I plug in x, okay, everyone, x equal to 2, plug in, x equal to 2, plug in, x equal to 2, plug in. So minus 4y squared, that is the first one, and then minus 0, 0, 0, good. And then dy, and then integrate 0 to 2, well, I hate this number, 32 minus 8 over 3. This is, damn it, this is hard. 32 times 3, this is 96 over 3. 96 minus 8, use calculator, 88, okay. 88 over 3, okay, and then minus 4y squared dy. Ta-da! This is easy now, right? Because, well, once you get back to this thing, this is the integration in 1 dimension. So simple. Am I right? So can I look at my solution that I compute it right? 1 second. Let me see the solution from the last year if I compute it right. X. Yeah, but the answer should be 48. So let's do if it is 48 or not. 88 over 3 y minus, so let's keep going. 88 over 3 you integrate with respect to y, so you get that, and then 4y squared, so you're gonna get 4y cubed over 3, and then you evaluate at y equal to 2 minus at y equal to 0. So 88 over 3 times 2 minus 4 times 8 over 3. And then the answer should be 88 times 2 minus 32, 144 over 3, 48. Yes, correct. Well, this is the answer. That it makes sense. So anyone have any question with our first example when we calculate the double integrals? So if you feel like you understand it, give me a reaction. You can, okay, good. One student, thank you. Did it. 3, yes, thank you. Sushanan, thank you. Pitya, thank you. Charlotte, thank you. Chantanipa, thank you. Yeah. Okay, about 10 students, you got it. Thank you. Good. Well, this is the easy one. And well, okay, one question in the chat now. Do we have to evaluate it with the x2? What? So again, so for those of you who do not understand, let's take a step back. Well, what we did is we integrate with respect to x first. This is what I did here is I already integrate with respect to x here. You can see I do not touch y at all. Y is the outside one. So I integrate with respect to x first. The yellow part here, this is integrate with respect to x. Integrate with respect to x here. Well, once I complete the part, then I integrate with respect to x. So I can, yes, now I only have y left. So, and then I can integrate with respect to y after. Makes sense? So once you get back to this thing, it's gonna come back to calculus 1. Okay, and hold on, everyone. So some of you are gonna ask me, Ajahn Krab, if I integrate this thing, integrate 16 minus x squared minus 2y squared dy dx. Well, if I do y first and then after I do x, does it matter? Well, the answer is, oh no, not 0 to x, sorry, 0 to 2 here. Well, of course, if you do this, switch the order, you're gonna get the same thing, 48. It doesn't matter which direction you're gonna go first. You can go x first, you can go y first, but the answer must be the same. Okay, for the case of the rectangle domain here that we learned today, it's easy because this is all numbers. So you can switch the order of integration easily. But what we're gonna learn after Songkran, it's gonna be a lot harder because you cannot switch it easily when you have some complicated domain. So sometimes the domain is not rectangle, it's gonna be something like a circle shape or something like a triangle shape or something that is harder than just a rectangle here. And that would be a big problem for integration because you have to change the number here. Sometimes it's gonna be something depend on x or depend on y, and that will make your integration harder. Sounds good? Okay, so well, we have about 20 minutes left, so I think we can do one more example or two more if you want, but well, let's look at 42 first. So let's spice it up. Well, we're trying to get familiar with the integration first, so after Songkran you can learn something more complicated. Okay, well, let's challenge yourself with another example. So example 42, this is still a basic one. So evaluate the integral, double integral here, x cosine xy dy dx. So this time I'm gonna do dy first. So the yellow part here, this is what I integrate. with respect to y first, and then I integrate with respect to x after. Well, start from what happened here. So I wanna, well, let's take the inside part first. So I wanna integrate 0 to pi over 2 of that thing. So I integrate with respect to y. So x is constant. So basically you can pull out x, you know, because x is constant. So what you can do, you can say integrate 0 to 1/2. I pull out x. You know, why not? xy dy dx. So what I'm trying to do is I'm gonna just work with the thing in the bracket first, because you know x is constant for that part. So let's kick them out. You know, kick the thing. Well, usually I kick everything that you know that does not depend on y. Kick those things out first. So this time we only have x here, so we just kick it out. And then next we're gonna say that, okay, let's do something inside bracket first. Do not touch the outside part yet. Okay. What happened here is you have cosine xy. So how would you do it? So integrate cosine xy. So it's gonna be integrate cosine, you get negative sine, right? Negative sine xy. But because of the chain rule, you have x. Am I right? Well, we're gonna come back to that thing and go slowly for everyone a little bit, because I know some of you already forgot it. Y from that and that, and then the x. So we're gonna take a look at this thing closely, okay? So some of you get lost already. So, well, let's take a step back. So when you integrate cosine y, so what do you get? So you get negative sine y, right? Well, if I say, what if I integrate cosine 2y dy? What do you get? Can you do that? So you're gonna say, oh, in Cal 1, Ajahn Ratinan tell us that you can change the variable. This thing gonna be integrate cosine u, because you pick u equal to 2y, right? And that means it's gonna be du by dy equal to 2, and that means gonna be dy equal to du over 2,ครับอาจารย์ and then this is going to be du over 2, and then you're gonna get 1/2 integrate cosine u du, and then you're gonna get 1/2 integrate cosine, you get negative sine u, and then plus c. Okay, and then I evaluate u back, so I get 1/2 times negative sine 2y dy, 2y plus c, something like that. Which means, you know, in Cal 1, the technique you do here, this is a basic substitution. Which means if you have integrate cosine 2y, so you're gonna get negative sine 2y over 2, right? The number 2 here come from the thing that you use a substitution. So that means, well, if you feel like you are more comfortable with the notation, you can say integrate cosine 2y d 2y. I'm okay with that. And then over to, well, some of you use this technique. This is okay, acceptable. And then you're gonna say this is actually, Ajahn, this is actually 1/2 times negative sine 2y. Okay, well, okay, plus c if you don't have the how do I say, the upper bound and lower bound of the integral. This is what you learn. So, and then, well, if I say integrate cosine 5y, what would I do? What would you do? So it's gonna be, okay, same thing. It's gonna be integrate cosine 5y and then d5y over 5, right? Well, everyone can do that, and then you get, okay, 1/5 negative sine 5y plus c. So if this thing is any constant, the thing that I dot here, any constant, like if I have integrate cosine ay dy, well, basically you should get 1/a times negative sine ay plus c, right? Simple. Well, if you feel like you cannot do use substitution here, you're gonna be in trouble for sure, because this is a basic from Cal 1 that you need to, well, I assume that you can do this thing from Cal 1, you know, this is a thing that you cannot forget. So which means if I face integrate cosine xy, well, but x is constant, everyone. X is constant, so you just, yeah, it look like cosine to y, something like that. So I'm gonna get negative sine xy and then over x. You know, if you feel like this is way too fast for you, go slower. Well, but the speed that I am going to do in class, I can do this thing quick. And I hope that after 1 or 2 weeks that you learn with me, you're gonna do this thing quicker, because this is a basic from Cal 1. If you use substitution every time, well, this question gonna take you 10 minutes. Impossible. You know, like if you have to, oh, pick u equal to x, y, well, it's okay for beginners. But you know, after you do it multiple times, you should learn how to do it faster. Like sometimes it's like the substitution, you can make the notation more compact and faster. Okay. All right, here we're gonna, well, this is good because x is gonna cancel out as well. So let's look at the next step, everyone. So before that, let's plug in numbers. So x, and then I'm gonna plug in negative, well, I plug in y now, sine pi over 2x over x, and then negative again, sine y equal to 0. I love 0. So, sorry. Okay, I didn't do anything other than plugging in everyone. So the thing inside the bracket here, I plug in pi over 2, I plug in number 0. So look at it again here, y over 2 and 0, I plug in it. And then, well, this term, yeah, this is 0. And then this term, whoop, you know, if you don't like it, pull out 1 over x first, gonna cancel out. But well, let's go slower than that. So integrate 0 to 1/2 x times negative sine pi over 2x over x dx, right? Wow. Looks simple now. X cancel out. So you're gonna have integrate 0 to 1/2 and pull out negative sign. So sine pi over 2x dx. And then now, am I right? So integrate sine. So you get what? So integrate sine. So you're gonna get well, integrate cosine, get sine, right? Okay. Why isn't anyone integrate cosine, get sine, right? So I think I missed the formula because I talk too fast. Sorry. So again, let's come back to that thing. So integrate cosine, get sine. Yeah, thank you for some of you who stop me in the chat. So integrate cosine, you get sine. So this is no negative sine. Sorry, everyone. Whoa, I talk too fast and this no negative sine. Okay, thank you. All right, if that is all, okay, I delete negative sine, 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 and delete negative sine. Okay, sounds good now. And then now I integrate 0 to 1/2 sine pi over 2x. So this time now I'm gonna get negative cosine. Okay. Yeah, because integrate sine, you get negative cosine. Pi over 2x and then over pi over 2. And then now I evaluate at x equal to 1/2 minus x equal to 0, which means I'm gonna get negative cosine pi over 4 over pi over 2, and then minus cosine 0, and then over pi over 2. You know, and if you simplify it, so you're gonna get 2 over pi. Negative cosine pi over 4 is negative square root 2 over 2, and then cosine 0 is 1. So this is plus 1. Okay. All right, that is correct. Match with the answer that I have. So sounds good. All right, sorry for that speed integration, and then I missed the minus sign here, well, but indicate cosine, you get sine, indicate sine, you get negative cosine. Yeah, I missed that thing, but well, I fixed it already. Good. All right, any question on this example? So a bit harder compared to the previous one because you have the term cosine xy here, which make you a little bit complicated because you need to use a substitution from calculus 1. Any question? Any question? All right, tell me the reaction if you understand it. So let's see how many people understand it. 1, 2, 3, 4, 5, 6, about 10 students again. Okay, good. So yeah, think about 1/3. About 1/3 of the class, understand this one. Thank you. So this is not well, this is your first day of the integration thing. So the take home point for today is make sure that you learn the basic integration already. So if you want to be more confident about the content that we're going to learn after Songkran, so make sure that you learn how to integrate this thing. So I don't want to say memorize, but well, practice a lot so you can absorb this formula into your life, and then also be sure to know how to use U sub, because when you have to do a basic substitution, you need to do it, and when we come back after Songkran, we're gonna look at more example 43, and then also we're gonna move to double integral over general regions, which is going to be the domain is no longer rectangle, and when you integrate it, it's gonna be well, let's say if you looking at general regions, when you integrate it, it's gonna be, yeah, you see, when you look at the general region, the region is no longer rectangle, and it's gonna make your how do I say, the integral side to be more complicated, because in that case, let's say you have integrate y from 0 to 2x and x from 0 to 1. You cannot do like you did in rectangle domain, because you cannot say 0 to 2x, 0 to 1, and then dx dy. Here it is wrong, because when the domain depends on x or y here, you need to be careful when you switch it. That is what are we going to learn. And one more thing before I let you go today. So you can see that this type of question, it's a lot easier if you do dy dx. Some of you are gonna say that, Ajahn, what if I do integrate x cosine xy, and then I do dx dy here, and then you do x first from 0 to 1/2 and y from 0 to pi over 2. Well, if you can do it, and the answer going to be the same. 2 over pi negative square root 2 over 2 plus 1. The answer going to be the same. But you can see that this thing is more complicated, because if you do x first, this is not constant. This is not constant as well. So what would you do when you say integrate, when you see integrate x cosine xy? What would you do? Anyone remember? Integration by parts. If you have polynomials equipped with trigonometric function, no way you can integrate it except by part. So you have to use integration by parts. Terrible. I don't want to do that. So this way you can avoid by part if you start from y. But if you do x first, do by parts, and then you don't know what you're gonna face after you integrate x, because you need with respect to y another time. So sometimes it can make a huge difference from switching dy dx to dx dy. This type of problem, dy dx easy, dx dy hard, but they give you the same thing, same answer. You know, sometimes when you see the question and you can switch the order of integration if you want. If you feel like if you switch it, the world gonna be a lot easier for you. Like if I put this question on the exam, I can put the x dy here. And if you don't know that you can switch it, you're gonna do this way. And you're gonna feel like, oh, Ajahn, this is so hard because I cannot remember by part. Well, that is because you do not switch the order of integration. If you switch it, yeah, no need to by part. You just do your substitution. Does it make sense? Yeah, well, you're gonna absorb this technique. I hope that when we come back from Songkran, 2 weeks that we're gonna learn, you're gonna absorb the technique more and more and more and more, and you're gonna get ready for the final exam. Hey, sounds good. That is all for today. Any question?